Oscillations by Michael Cox, and he's our guest for a couple of days, and he comes from Durham University, which is in and famous for its rich students. But Michael made his master in Birmingham, and then he went to Edinburgh and made a PhD with Jacques Van Nest, which is our Mercator fellow, and it was about the scattering of internal gravity waves at a time-dependent balanced flow. And that is not the topic of this today's talk, but the work which he is doing now as a postdoc in Durham about phase averaging. Thank you very much.
Thanks, Carlos. Perfect. Yeah, thanks for having me. So I'm going to be talking about a numerical method for multi-timescale systems. It's called numerical phase averaging, and the novel aspect of it that we're introducing is the deferred correction method. So we're doing numerical phase averaging with deferred correction. I'll tell you all about that in the talk. This was work I did with Hussein during a postdoc. It's now finished. It was earlier this year. So yeah, this was my most recent work with Hussein at Durham, and that was my walk to work. So it's a very nice place to be. Yeah. I'll start by outlining what phase averaging is, and then I'm going to implement phase averaging with a system called the swinging spring, which is a multi-timescale system. It's commonly used as a toy model for phase averaging. So I used it because it's the one that a lot of people use in literature, and it's got a lot of timescales going on. So it's an interesting thing to play about with. And then I'll outline our deferred correction method and revisit the swinging spring with this deferred correction method. And then the swinging spring is actually quite complicated. So at the end, I'll talk about a simpler ODE that we've also implemented this method with. So the type of system we're concerned with are oscillatorily stiff systems. So by that, I mean we have a time evolution. There's a linear and a nonlinear part, and the linear part is much bigger than the nonlinear part. So you have very quick linear oscillations that are modulated by some nonlinear behavior in the background, as in this schematic. So a geophysical example of this would be the rotating shallow water system, which I'm sure many of you are familiar with. So the big U here is a vector of our system variables. So in the rotating shallow water system, this would be the horizontal velocity, u, little u, and then h, which here is the height perturbation. Sometimes you'll see it as the whole layer height, but it's basically the change in height from a mean height, big H. And you have these linear modes that are dependent on the Coriolis parameter f and gravity and the layer height. So that's your fast oscillations in this system. They're internal waves. And then the slow modulation is coming from nonlinear terms such as advection and this term from the mass conservation equation. And in practice, what it means when these linear terms are much bigger than nonlinear terms in this system is that we have a small Rossby number. So an example of where phase averaging could be used is with this system with a small Rossby number, or for example, the 3D Booster-Nash equations with a small Rossby number, wherever you have these multi-timescales going on. So these fast timescales, these internal waves, they impact the slow timescales in a system. Often we're interested in what's going on in the long term, but in order to accurately model these slow long-term dynamics, we have to resolve the fast linear modes as well. And computationally, this would require a small time step. So it's computationally costly. And if you take large time steps on the same timescale as the slow dynamics, you'd end up with an unstable solution. So what phase averaging does is it's a time average that filters out some of these fast oscillations while preserving their effect on the slow dynamics, giving you a more stable solution with a larger time step. And the way so I'll just outline the mathematical framework of phase averaging. So the way we represent this timescale separation is with this epsilon parameter. So in the rotating shallow water system, this epsilon would be the Rossby number. And this is a small parameter, so the linear term is much bigger than the nonlinear term. So to try and remove some of this oscillatory stiffness, we transform into something called the modulation variable. So this modulation variable, here we go. It's not dependent on this fast time scale here. And so you have this exponential phase in front of this slow modulating amplitude. And if you take the derivative of this expression here and sub it into here, you get this box equation at the bottom. So these two equations are equivalent. So the time evolution of the modulation variable is equal to this nonlinear part sandwiched between these oscillatory phases. So for this time dependence, we no longer have an order 1 over epsilon term in our evolution equation, which suggests a reduction in oscillatory stiffness. But if you took a time derivative of the lower boxed equation there, you'd still have a 1 over epsilon linear term. So what that means is there's still fast oscillations in this modulation variable. And what phase averaging does is we try and remove those fast oscillations. And the way we do it is by only averaging over these linear phases. So that's why it's called phase averaging. So to achieve this, there's a couple of ways you can formulate this. I've introduced a dummy variable S into the modulation variable definition. And that pops up in the fast linear phases. And that's what we're going to average over. And then because we've introduced this variable here, U is now a function of S, and the modulation variable is also a function of S. So your system variables and the modulated system variables are a function of this dummy parameter S. And S equals 0 gives you the full dynamics of the system. So we're going to average over this phase variable, like so. This is a bit of a notational nightmare, so sorry about that. I've put these overbars in to indicate that so we're just averaging this equation here, this box equation here. And I've put the overbars in to indicate that this modulation variable is now the averaged modulation variable. And there's an underlying assumption that it's insensitive to changes in this dummy parameter S, which is why it's no longer there's no S cropping up in this average on the right-hand side. So we average over the phases using this dummy parameter S, and the average is defined as a time integral between minus t over t2 and t over 2. So if this time interval was infinite, you'd be filtering out all of the fast dynamics. But we're using a finite interval. And we achieve this by using a bump function, a kernel, so this row of S, which decays away from the central point. And the best way to understand what this average means is to look at the various limits on big T, the averaging window. So if big T tends to infinity, then you filter out all of the fast oscillations in the system. And this is the slow asymptotic solution of the system. So in the case of the rotating shallow water variables that I showed you before, equations that I showed you before, this is quasi-geostrophic balance. So you remove all your wavemoids basically if you take an infinite average. If you shrink this averaging window to 0, your bump function here becomes a delta function. So you squeeze the sides and it becomes a delta function. And then what that means is you aren't doing any averaging and you get back to unaveraged equation here. So you resolve the full dynamics of the system. And then the limit we're interested in is this intermediate limit, somewhere between 0 and infinity, where you have this finite time averaging window. And this smooths out oscillations with a period of less than t. So you're filtering out some of the fast oscillations of the system.
Michael, this can be that for the infinitive t, the equation is valid. It's only for first order and epsilon.
Yes.
So the issue, or do you mean the full balanced state? Or?
So yeah, so it's only order epsilon. So strictly true when you have epsilon vanishing to 0.
But you can also write down the QG-like models with higher orders.
Yes.
That wouldn't be the same as T2.
No. Yeah, I think so. I'm talking about the slow asymptotic solutions. It motivates the shape of the. So the way it came from was people looked at the asymptotic limit and then they thought, what would happen if we take a finite average over that time? And then there's some papers by a guy called Anthony Peddle that look at the convergence of this average to the true solution. So there is some maths backing this up. It's not just what I'm showing here, but yeah.
The first order, it's the same.
Yes.
But for intermediates, it's not.
No. But I'll show you what that looks like in some of the simulations. So, yeah. So to recap, we start with the full system with this timescale separation, and we transform to these modulation variables modulated by quick phase, average just over the phases, and approximate this average with a kernel, a finite average with averaging window, and we approximate it with a quadrature sum. So this method of numerical phase averaging was first introduced by Beth Wingate and Terry Hall in 2014, and they proposed the phase averaging solution to be a coarse propagator in a parallel in time method. So that's what this diagram from their paper at the bottom demonstrates. So the red line here is a coarse approximation using phase averaging, and then what they propose to do is to run finer grain simulations from each of those points, each of the coarse solution points in parallel, and then correct those solutions with your corrections. So yeah, they proposed it as a coarse propagator, but it's also useful as a numerical method in its own right, and there's quite a lot of literature since demonstrating that. An interesting example is this paper by Yanzaki, Kotter, and Wingate, where they used phase averaging to solve the shallow water equations on a sphere. Yeah.
You need the predictor, the red line. You should also just start from the point and then run parallel equations.
The predictor will give you the initial condition. So you're computing these across different cores, each of these. So the predictor gives you the initial conditions for your correction, right?
The correction does what? The big point to the black point.
Yeah, I'm not too sure. I can't remember. Sorry, I'd have to look at the details. Yeah. I can't remember. So the example I'll demonstrate phase averaging with before moving on to our numerical method is the swinging spring. So what you have is a pendulum that can rotate in 3 dimensions, that can Yeah, it can move in X, Y, and Z because it's also got a spring on the end. So you have the changing length of the pendulum from the spring. So you've got an oscillation from the spring, and then you've also got a pendulum in the horizontal plane as well. I've skipped a few equations here to put it into the form of the equations that I was showing you before. But X here is a complex variable that is equal to the displacement of the center of mass of this pendulum bob plus an imaginary part, which is the momentum of the pendulum bob. So your system variables consists of the displacement and the momentum of the pendulum. I'll just show you plots of the displacement. And then you have a linear part that is dependent on the frequency of the pendulum, and then this alpha is the ratio of the spring and pendulum frequency. So you have two frequencies, one from the pendulum length and the other from the frequency of the spring. And then this lambda is determined by the things like the spring constant and the length of the pendulum, but is essentially the strength of the nonlinearity in the system. And what does this look like? So these are the trajectories of the swinging spring. So in the black lines here, I've plotted the modulation variable of the spring. So this is the slow modulating part to the fast linear amplitudes, and then the full solution is the grey bit in the background. This is a phase plot of the horizontal displacement, and then this is the vertical displacement against time. And probably the most interesting thing to point out here is that this modulation variable in the vertical displacement, what you can see from the zoomed in section is that there's variations on the same scale as the fast linear oscillations. And so it's quite a difficult system to resolve. You also have a second time scale coming from some nonlinearities, and then a further damping over another time scale. So you've got multiple time scales in the modulation variable that make this a difficult system to resolve numerically. So we run phase averaging with a few different averaging windows, and you can see that it's quite successful. So these are trajectories of the X, Y, and Z displacement of this bob against time. The dotted black line is our truth. So that's a very small time step RK4 simulation, and that's what we compare to. And then the other three use a forward Euler method. And you can see that, so t equals 0 corresponds to no averaging. And you can see that, there's these oscillations in the approximate solution that aren't in the actual solution. And it's very unstable. So all three of the variables move quite quickly away from the truth solution, this black line. And then what the phase average solution does is it removes these oscillations, so you have a closer, a better approximation to the truth solution, and it's also made it more stable as well. So it sticks closer to the truth solution for longer. So we've increased the stability and the accuracy of the solution by averaging in time.
There's no parallel computing, right? There's
no.
Discretize this phase average equation.
Yeah. Yeah.
With the same time step as the
Exactly. Yeah. And then another feature of phase averaging is that there's an optimum window for averaging. So the papers by Pedal that I mentioned earlier, they show that there is an optimum window for your phase averaging that gives you the best approximation of the dynamics of the system that you're looking for. And that's demonstrated here. I've plotted the relative error of the system. So it's the root mean squared error up to t equals 100, so up to this point before we start getting some instabilities.
Michael, can I ask a question?
Yeah.
So the difference, so the blue line is without any phase averaging.
Yeah, yeah.
But it's different from the real solution. So the real solution, the black line, this is just run with a different time step. This is a difference.
Yeah. So the real solution's with a much smaller time step, and it's with a RK4 method, so it's more stable as well. So
then also your phase averaging solution depends on the time step. If you decrease the time steps, then the blue line should match the black line in time.
If you increase the time step?
Decrease.
Yes, yeah, exactly, yeah. But what I'm demonstrating here is that the blue line has the same time step as the phase averaging lines. So I'm demonstrating that without averaging, you lose accuracy. You gain accuracy and stability through averaging, even using the same time step. So you could reduce your time step, but by phase averaging, you're reducing your computational costs because you don't have to. Yeah.
Time step would the line also get better, or is that not?
It's a good question. I think it depends. So because you've averaged, not necessarily. Yeah.
But the same averaging.
So to a point, yes, and then I think it stops. So because you've averaged out some dynamics, you're always going to get a better solution if you just use a very fine time step with no. If you resolve all your linear dynamics, that's your best solution, basically. So if you've done some averaging, you're not going to get, you've lost some of those linear dynamics, even if you use a smaller time step.
For certain small data.
Yeah.
And these deviations at the end, what are they, Oscar?
The deviations?
T100, there's a large difference.
Yeah, so eventually the phase averaging solution here also becomes unstable as well. Yeah. But why?
That's unstable. Stable.
Well,
unstable.
Okay, not unstable, I guess, but it's moved to.
Doesn't work.
There's some cumulative error going on. Yeah.
It's a chaotic system, right? And
yes.
Small perturbation after some time will always lead to bigger errors.
Yeah. Well, it depends, doesn't it? Like to a point, but it works better for longer times than the unaveraged system. So you're gaining something from it.
Line also stays close to it. At the end, there's not much difference in the deviation.
Yeah, that's true. Yeah, maybe it's not the best example. Yeah. I've not got better examples in this presentation, sadly. There are better examples, so yeah. I mean, one thing I also realized was I've given an example here with two different averaging windows, which gives the same result. And actually, from this, you see that the error does change with averaging window. So I'm not quite sure why I've done that either. If you want another flaw with this slide. Yeah. Pretty optimal, yeah. So if it's t equals 1.4, so you're looking at like the lowest relative error, yeah. So this is the relative error across the whole, well, up to t equals 100 before you get this divergence. And you can see that an optimal exists. One thing that this slide, again, doesn't demonstrate, but there are different optimal values for different variables. So because x and y have a similar optimal variable, but then z, because it's oscillating at a different frequency, may have a different optimal averaging window as well. And the degree here is the degree of the polynomial in the quadrature sum. And the reason I plotted that is because when they start moving away from each other, that's when the quadrature sum is no longer well approximated. So we're limited, at least with this system, to around the t equals 1.5 point. But the take-home message, I guess, is your phase averaging does increase the stability and the accuracy of your solution. That's why people use it anyway, and it allows them to take larger time steps in simulations. So our motivation for combining numerical phase averaging with a deferred correction method is that we aim to further improve the accuracy and the stability of phase averaging. As you saw, there were some issues with the slides I showed. And I don't parallelize the simulations I'm showing, but one advantage of deferred correction methods is you can parallelize the correction and the prediction. So your computation time is not vastly increased because you can distribute it across different cores. And the other thing I'd like to get from this method, which again is hard to see from here, is decrease the sensitivity to the averaging window. So you have an optimal averaging window, but you don't necessarily know what that is. So we're hoping by implementing deferred correction methods, we reduce the sensitivity to the averaging window. So what is a deferred correction method? So a classical deferred correction method is you compute your approximation across endpoints, and then you'll interpolate that approximation with a polynomial. So you form a continuous solution across those points. And then using that interpolation polynomial, you can estimate the error on your solution at each time step and correct your initial approximation with that error. And I'll show you how that works in
time numbers. Times.
Yeah, that should be times. Sorry. Yeah. Yeah. So the polynomial is through points in time. Yeah. Yeah. So the outline for implementing a deferred correction method with phase averaging is we start with our modulation variable equation. And then we'll calculate the m values of our modulation variable using phase averaging and our initial window T1. So that's just what I showed you before with these trajectories. We're using that as our initial approximation. If we define the error as the difference between the exact solution and this interpolating polynomial, we can take a derivative of this solution, of this error, sorry, to get the following equation. So it's just the time derivative of the exact equation minus the time derivative of the polynomial. And then because this exact equation satisfies the box equation at the top, you can substitute this back in to give you the time derivative of the error is equal to this nonlinear term minus the time derivative of the polynomial. And then because we don't know the exact solution, we substitute in the polynomial plus the error into the nonlinear argument. And then I guess the novelty of what we're doing is we're using a different averaging window to average the error as to the averaging window we use for the, it's clearly not a fan of phase averaging, the averaging window we use for the initial one. And then we correct.
Don't know the data.
Sorry?
Don't know the data.
Yeah, exactly. So the way, like, you take the time derivative of this equation to get to this equation, and then you substitute back in this bit here, and instead of the data, you rearrange to give yourself the error plus the polynomial. So you're solving to find the error as well as solving to find the. So you start with an initial value, and then you time evolve the error as well as the time evolve. Yeah, I think 0, and then it grows as your, yeah. So you have to run it for a little bit before you start correcting the error as well, so you have enough points to predict the error in the first place. Yeah.
The quality of this method will depend on the actual choice of.
Not so much, I think. Not so much. Yeah. I mean, you start with a 0 error and then it grows, and I think yeah. You're not starting with like a huge error.
Error. Assume the error.
Yeah. Yeah. There's errors in approximating the error for sure. Yeah. So this schematic demonstrates how the predictions and corrections are computed. So, for example, here we're using 4 values of the prediction to compute 1 value of the correction. So, and then that correction value can be used to correct the prediction. And you can stack these corrections in parallel so that you improve the accuracy without increasing your computation time. So this is the phase averaging with deferred correction implemented. So these are exactly the same as the trajectory plots I showed you before. So the averaging window we use is 1.4. So it's the optimal averaging window I showed you before. This is just the unaveraged version. And then we use a second averaging window, which is quite similar to the initial averaging window. And you can see that the deferred correction step brings, so the just regular phase averaging, the green one, you have some errors developing, and the deferred correction step brings you back to that truth solution. So there is an improvement in error and stability from this deferred correction step.
The green line is the previous method, and the orange line is the deferred correction.
Yeah, I mean, yeah.
Always better. The X variable there's at T250 a larger deviation of the orange line.
Whereabouts?
X A LA T250 orange line.
No, because this is the truth solution here. Yeah.
So orange line is always closer to the dashed line.
Well, no, and I'll show. So, I'll show you that in a couple of slides. So
here.
Yeah, for this slide, yeah, and the next slide as well, yeah, but not this slide. No. So I was arguing that one advantage of this might be you might not know the optimal averaging window in advance, so you could use 2 different averaging windows. So here we've started with a suboptimal averaging window, which is this T1 0.6, and you can see that the phase averaging method is much worse than in the previous slide. You have these oscillations coming in somewhere between the true solution and the forward Euler solution. And with a different averaging window and this suboptimal initial averaging window, the deferred correction method again brings you pretty close to the truth solution. And I think I can claim on this slide it is better than the phase average solution. So there is an improvement that we see. What we then did was we were examining how varying the second averaging window would change the overall error and see if we see an optimal error in the second averaging window. And we do, but it's not the results that are necessarily what we wanted. And I'll explain why I think this might be. So if T2 goes to 0, that's the same as just taking a deferred correction step. And what's without any second averaging. And what's weird about this is these dotted lines here are the phase averaging with no deferred correction steps. And bizarrely, the deferred correction step seems to decrease the accuracy of the system for smaller averaging windows. So that shouldn't be happening. Yeah. But you do get an increase in the accuracy for larger second averaging windows. So as you, for example, if we look at an initial averaging window of T1 equals 0.6, you start with a worse approximation, and then as the window grows, you end up with a much better approximation.
Is it because of the overcorrection?
Yeah, I think what's happening is potentially the, there's either some overcorrection, or because the initial solution is not as good an estimate when you do an unaveraged deferred correction step, you're not necessarily tending towards the underlying dynamics so well, yeah. But then the other thing that I've noticed was this doesn't really agree with my previous plots, and I think it's partly to do with where we're computing the average as well. So these are computed up to t equals 100. And I think if I did these plots over a longer time, you would see this phenomenon would disappear. Yeah, but I don't have those plots, sadly, because the phase averaged solution will become unstable, whereas the deferred correction method's more stable in the longer run. So we looked at this and we thought, what can we do? Well, we thought we'll use a simpler system to see if we get an improvement with a simple system, and then can return to the swinging spring afterwards to try and work out what's going on. So the simple ODE is very similar to the swinging spring. You have fewer variables, so we've got rid of the Z variable. And these X and Y's again have a real and an imaginary part. You've got two frequencies, which we've separated in time more significantly this time. So there's something like 60 times difference between the omega X and the omega Y frequency. And then you have two different strengths of your nonlinearities, and they will drive the modulation of the linear frequencies. So the dotted black line again is our truth simulation, and then we have the forward Euler, the phase averaged, and then the phase average with deferred correction. And you can see in this case that the phase average with deferred correction is outperforming the other two, and the phase averaging does reasonably well, and then the forward Euler is the worst of the three. Yeah. And then if you look at the error plots, you get something more reasonable. So you're not getting this initial increase in error from the deferred correction step. You're getting a decrease in error. And then you even see this optimal second averaging window cropping up, most notably in the Y variable. So we have that the deferred correction step is improving the accuracy of the solution. Yeah. No, this is with second average. This is the
T20, that's not second.
Yes, so so the deferred correction, but I mean, that's what we would expect. That's why I was a bit perturbed by the other plots where you have this increase in error to start off with. So you would expect the deferred correction to reduce the error to start off with, and then the averaging further decreases the error. But as you said, this is also an issue because, I mean, for example, for this X variable, you're basically as well off just doing a deferred correction step with no averaging as you are to doing any second averaging. Yeah. Yeah.
Yeah, what's the difference between X and Y here? Is one the slow and one the fast variable, or?
So they're both modulation variables, so they're both the modulating amplitude to these linear frequencies, but then yes, Y is faster than X. Slower than X. Yeah, I'm not sure why this is X as well. I'm assuming that's why, yeah.
So, but then X is your fast variable at a higher frequency.
Yes, yeah. Yeah, sorry, yeah, X is the higher frequency, yeah. So, yeah. So numerical phase averaging does filter the fast oscillations of a system whilst preserving their effects on the slow dynamics. Hopefully you're convinced of that. Maybe not, but I'm not the only one saying that. And that was the first part of the talk. So our aim was to combine this with a deferred correction method to increase the accuracy and stability by further filtering these fast oscillations. And you do see this in these trajectories. But we do have issues. The issue being, I'm not sure how effective the secondary average is. I mean, in these plots, averaging a second time is not too beneficial. And this increase in initial average is somewhat confusing to me as well. So I'm interested to hear what other people think about this as well. In terms of next steps, we want to implement this with an integral deferred correction method. So you solve an integral equation for the error instead of a differential equation, and this is more stable. So we're expecting that to improve the accuracy of the solution. And eventually we'll apply it to a rotating shallow water system. So I do have a phase average rotating shallow water simulation, but without the deferred correction. It was for a different averaging method that we were investigating. So we'd like to apply this again to the more physical solution of a rotating shallow water system. So it's very much a work in progress. Yeah, thanks very much. And please let me know if you have any questions. Yeah.